So, the title of this course is Complex Analytic and Algebraic Geometry. And I should comment at the beginning that probably we will be going toward a study of objects of an algebraic nature. However, in order to build the theory about these manifolds or objects, varieties, or whatever they are, requires a great deal of preparation. On the other hand, the preparation for the study of analytic objects is much easier to present, and in the end we may use both because we are dealing really in the complex case. If we were dealing here with finite fields and so on, maybe my opportunistic view of how this subject should be presented, just use any method I want, would not be appropriate. But we're dealing here with algebraic geometric objects over the complex numbers, which have automatically a complex analytic structure. So why not use the analytic structure? So we will simply start with the analytic structure and note all along which examples are algebraic, and in the end we will start to build up the notions of algebraic geometry. In any case, we will have many, many examples which are fundamental for the subject of algebraic geometry. I should mention two things. One, the first reference, which is very good from my point of view, is the book of Phil Griffiths and Harris, which is nowadays an old book, but it's called Principles, I still like it, of Algebraic Geometry. I think this is it. There may be several versions. The first version, I think, was published rather early, maybe in 1978, but maybe you can find more recent versions. There are a lot of small mistakes in this book, but not too bothersome. It's really an excellent book for this point of view that we have in this course. I would also like to mention a principle here, which we call Gaga principle. This is not Lady Gaga principle. This principle of, in my bad French, is géométrie analytique et géométrie algébrique. It means of Jean-Pierre Serre. It means that in certain situations it doesn't matter. And in fact, in every situation that we will be dealing with of a global nature, global compact nature, the objects which we will be studying, every theorem of the analytic type really proves automatically a theorem of the algebraic type and vice versa. So we take the easy route and start with analytic objects, and we begin therefore with a definition of a complex manifold. Well, all of you are familiar with real manifolds, so this thing is a real manifold. For me, it will always be paracompact, I think. And it will be covered by a coordinate chart, so it has an open covering. And the local coordinates, which are of course homeomorphisms, Hausdorff space and so on. Homeomorphisms in some Cn. Then we talk about an n-dimensional complex manifold. Of course, it could be disconnected and you'd have to have different Cn's, but I'm not going to worry about that right now. And the change of coordinates should be bihomomorphic. Should be, is bihomomorphic. Means the maps involved are holomorphic and their inverses are holomorphic, locally given by holomorphic functions. The standard picture I'll draw and everybody has in his head, you have these u alpha and u beta, and then you have here something like Cn, v alpha and v beta, and this intersection go up and down here. This mapping is called phi alpha beta. So the assumption is phi alpha beta in bihomomorphic form. And of course, any compatible system of coordinates is allowed. So if you, for example, refine the coordinate system and take other coordinates which are holomorphically compatible, it's allowed. So we go to the maximal thing. Here's the phi alpha. Here. Okay, that's a complex manifold, and we will be dealing with problems of a global nature or complex geometry, trying to understand these global complex manifolds and the related function theoretic or cohomological objects on these manifolds. And many of them, as I said, in fact, most of them will be, in fact, algebraic things. Now, I use the word global as opposed to local, and I want to tell you what I mean by an example of local and global. Versus global. So we are on the right page on this subject. Let me define, first of all, a global object. An example of a global object is a meromorphic function. Now, it's defined as a collection of locally compatible, local holomorphic, meromorphic things. So let's write that down. So what's going on here? So let's say a meromorphic function m. So m, what is it? What is it? Well, first of all, you have a covering, maybe not a coordinate charts, I don't know. And on each chart, you have two holomorphic functions. So let me just write here, the way I'm thinking about this is a quotient of two holomorphic functions on each chart. And of course, whenever possible, I want to assume these things are locally, they have no common factors here, Tyler free divisors. And you usually can attain that. So some reasonable, relatively prime condition on these functions. And you have some compatibility condition. So if you restrict m alpha to u alpha beta, you want that to be the same thing as restricting u beta to m alpha beta. And of course you have to write this in terms of these functions. That means f alpha g beta minus f beta g alpha is equal to 0. And that's a representative of a meromorphic function. You see that it's compatible, it's globally defined, but locally it has a good representative, but it doesn't say that globally it has a good representative as a quotient of holomorphic functions. This is really just a representative because you want to allow refinements or other covers which are compatible and other representations which give you the same function, but it's some obvious thing that you need to do to define what the meromorphic function is. So in reality, it's a meromorphic function is represented by something like this. object. Let me tell you how global it is. Let's recall one complex variable. One variable, one-dimensional theory. And I will do a lot of one-dimension here. So suppose you take something like the Riemann sphere, which everybody knows. You know how to deal with this thing with the two usual coordinates, the z coordinate, the zeta coordinate. We'll talk about this in great detail. Everybody here knows about this thing. You have 0, here's the sphere, it's really a copy of S2, and you have 0 and infinity. It is compact. So there are no global holomorphic functions except for the constant. So x compact, the general statement, implies that there are no holomorphic functions except for the constants. Of course, I'm assuming here connected, otherwise you can do something stupid. Okay, so there's nothing holomorphic thing. In particular, m equals f over g globally gives us just the constant function. So there are no global, essentially no global meromorphic functions of that type, just the constant functions. But there are many meromorphic functions. For example, the function m of z on the one chart that you know equals z is a meromorphic function, which of course has a 0 at 0 and a pole of order 1 at infinity. So this is really a meromorphic function on the Riemann sphere. But it can't be represented globally as a ratio of two holomorphic functions. So here's an example where global theory and local theory is completely different. We are interested in global theory, although we need to do some local theory. Let me give you an example of a local theorem in one variable in dimension 1. You'll see what I mean by local versus global better there. So for example, if you take a function holomorphic, as an example, on some domain in the plane, so some mysterious domain, and you say 0 is here to make life easy, and let's say that f of 0 is 0, so we have it all normalized, it doesn't matter here. And of course, f is not identically 0, so I'm interested in a function which is not constant. Then, there's a number k, which is, we talk about the order of f, the order of vanishing of f at the point 0, so that, in fact, after change of coordinates, so by holomorphic change of coordinates, which we allow because we're dealing with manifolds, so after biholomorphically change of coordinates near 0, no, not globally, f of, say, w, new coordinate, is equal to w to the k. So in some sense, every holomorphic function is just w to the k, where k is the appropriately defined vanishing order of the function at that point, or polar, if it's meromorphic polar. So you see, the local theory is really trivial in this case. Whereas the global theory, understanding global holomorphic or meromorphic function, not so trivial, even in dimension 1. I want to mention also in higher dimensions the local theory is also non-trivial. Is much more difficult, much more important, and much more difficult to understand. Much deeper. Let's say much deeper. And the reason it's much deeper is that the set where a function vanishes locally is see the set where a function vanishes here locally is just a point, and all we need to do is say what is the multiplicity of vanishing at the point. But the set where this vanishes is one complex dimension. And the thing is, it can have singularities of a complicated nature, even in a two-dimensional setting. So my favorite example, so that you see this, and you can look at it yourself to have some fun with this example, is in 3 variables. So it's a two-dimensional thing that I'm going to write down with an equation. Say, let's call it C for cone. Say x, y, z in C3, such that z squared equals x times y. So z squared minus xy equals 0. You see the differential of this function here at the origin vanishes. So there, at least from that point of view, there's a singularity. And in fact, it's quite a singularity because this is a cone. And you see if you multiply each of these variables by t, it comes out t squared. So it's a homogeneous polynomial of degree 2. So it's invariant by dilation, by the usual scalar multiplication. And that means that at the origin, here's the origin, all these lines are in it. In fact, it looks like it is somehow a cone over a conic at infinity. So this point is a highly non-trivial singularity, actually. One could have some fun analyzing it here. The set itself has some singularities, whereas in one dimension, the set itself has no singularities. So to close this introduction, I emphasize the 2 points of view, analytic and algebraic. I emphasize that we will deal primarily with algebraic varieties or algebraic manifolds, but we will allow ourselves analytic tools, at least at the beginning, because it's much easier to get into this stuff with the analytic methods. And at the end, we will also mix, but we will, in fact, have the advantage of gaga, which means everything algebraic is really already analytic, and well, that's clear, but everything analytic being algebraic is not so clear, and we will use that principle many times. I explained what is a global algebra, I explained what is a complex manifold, and I explained the notion of a global thing, named a meromorphic function, and I explained that you have to have non-trivial considerations here because there are no, in the compact case, there's simply no holomorphic functions on the compact manifold. So you really have to define meromorphic in this way. And there are very interesting questions, global questions about, for example, meromorphic functions. Compact case. I pointed out an example of a local theory which is very simple, namely one variable, that if you normalize correctly, every function of one variable is just w to the k or something. There's nothing to prove. It's a beautiful theorem and very useful, but it's not deep. But in higher dimensions, there are problems with such local things. Even if you localize here in the neighborhood of the origin here, the singularity, you will see that there is even non-trivial topology happening here. If you intersect this with the sphere here, you actually get some really interesting non-trivial topology, this intersection with the sphere here that you would not get in the smooth case. So let's get on with it to the body of the course. So that was a little break so that we understand all this mathematics. Now, examples. So just a few first examples. So the basic example of algebraic geometry in algebraic geometry are projective spaces. Okay. Now, my notation is the following. We start with a complex vector space. Here everything is finite dimensional. And we go to the associated projector space of that vector space. I will explain this, but this is just notation. You start with a complex vector space, and you go to associated projector space. Well, what is this thing? This is the set of W, so that is a one-dimensional subspace of the vector space. So all possible one-dimensional subspaces of the vector space. Actually, while I'm at it, other class of important examples, let me just mention the so-called Grassmannian k-dimensional subspaces. Here k is the dimension, so it's not like that. So these are the set of W, the same thing, a k-dimensional subspace. Before going on to discuss this in some rigor, let me just say why, an example of why you are interested in these things. Suppose you have a curve, just a simple matter, a curve in C2. But this should be a complex curve. This means locally parameterized holomorphically by a holomorphic map. By the way, I draw this all the time as if it's a real curve of one dimension, so please don't get confused by me. If this, when I have a little piece of this, you have to understand that this is a disk. I always draw like this. Okay? So there's no, why not? So, if you have such a thing, if this is a curve, then at each point you have its tangent line. Now you can think of that tangent line as you do in elementary mathematics. I talk about it based at the point of the curve, but this is really just a one-dimensional vector space. So this is a tangent space at the point of this curve. And you notice that you have a map, which some people call a Gauss map, which maps, so this, let's say this curve is in C2, so it maps the curve to the projective space of C2. The map takes the point P to the tangent space at P. You see, as the curve moves, this is geometry, as the curve moves, the infinitesimal information moves. You're losing some information here, but you have a huge amount of information. This is the first order information about this curve as you're moving along. So you see, you need to understand this projective space. So that's an example, or this is a manifold, and you have the tangent space of the manifold and so on. This is an example which I call, maybe it's not exactly, Gauss map. So you really need these projective spaces, or in higher dimensions you need the Grassmannians. This is just an example. So these are, the way I've talked about them now, these are just sets. I think I should try to, I'm sorry. If I were taller, it would be better. Okay, so these are, let me just state this and then I'll discuss it. These are compact complex manifolds. where for natural coverage, so natural, whatever that means, charts, the change of variables, change of coordinates, is very, very, very simple. I will show you, but let me just emphasize qualitatively what the point is our rational, so there are many of them, our rational maps. I will show you what these rational maps are. You understand what I'm saying? In my first picture, I have these little things here. You see these little things, and the change of variables is biholomorphic. That means that power series development and all of this stuff. But here, these charts are very, very big, and the change of coordinates in these charts are rational maps. So you should feel we're coming close to algebraic geometry, because rationality is something that occurs in algebra, quotient of two polynomials, right? So so this is coming near to algebraic geometry. Okay, let me tell you about these charts. So, I think I have room here. You must learn to think about the notion of genericity. So there are several things you must learn in mathematics. One thing is somehow, what does it mean something's in general position? And what does it mean to move from something special to something general? What does it mean if you're in general position, you can move it and it stays in general position? What does it mean small? What does it mean big? All of this formal mathematics that has been pushed down your throats is valueless unless you have these kind of qualitative understanding of the subject. So, for the case of the Grassmannian, for example, let me call it U be a subspace of V of dimension n minus k. So I'm now in the Grassmannian. Grassmannian means k-planes, k-dimensional subspaces. Please see a subspace. That's a subspace. Now, I want to talk about, what does genericity mean? It has no meaning at all. Genericity is something with respect to something else. So, now I have something else. So you see I have something standard that is given here. Maybe I'll write here U0, okay? Right? So maybe if you want, take coordinates, take basis, E1, E2, E3, you know, so Mickey Mouse basis, E1, E2, E3 to En, and we're talking about k-planes, so the first k basis elements, then we take ek plus 1 to En, and that spans a special n minus k plane. Yeah? Now I've got an n minus k plane that's somehow there. And now what does it mean, genericity with respect to that n minus k plane in general position with respect to that? It means that it's complementary. W is in general position with respect to U0 if and only if it is complementary. It's completely clear. Because if I move it, it's still complementary. If it intersects in some positive dimensional space, and I move it, it doesn't intersect in a positive, right? You see that, right? Centel, is that?
Usually Does it mean that general position is like there are two subspaces and their intersection is of the minimal dimension?
That's right. So I fix sort of one, and I say the other one is in general position with respect to that if its intersection is of minimal dimension. Now here I chose something of complementary dimensions, so it means the intersection is just, means it spans, right? So, yeah? So here is U0, and here is say some W of complementary dimension, and what it means is, what Chantal was just saying, it means that if we move this thing, it means if we move this thing, it still stays there in general position. Right? Okay, so that's how I'm going to define the coordinate chart. Complete generality because projective space is just a one-dimensional situation. So a special case, but gross money. So let's say the coordinate chart. So the coordinate chart, I guess a chart is the coordinates open set with respect to this fixed U0. Well, it's just the set of W, so that W intersect U0 is 0. Isn't that a reasonable open set? It's open intuitively. I hope you feel, you see, there's no topology on this Grassmannian until I tell you what an open set is. I just told you, given say some W0, which is complementary, I've told you what an open neighborhood of it is, a huge one. All of the things you can get by, you see, I started with some W0, which is complementary, and now I get all of these possible movements which are nearby. Now, believe it or not, this is a vector space. Actually, you should think of it as an affine space. So this, what is this? This is naturally isomorphic, let's see here, to something like, okay, I think I want to write this HOM of W to U0. Well, let me write it where W0 is some special complementary space. Any particular complementary space. And now let me explain to you why that's the case. Yes?
And W here is definitely a complementary dimension, because only from that definition you could have any dimension less.
No, I'm talking about, I maybe didn't say it explicitly, but I'm talking about the Grassmannian. So I start with an n minus k dimensional space, and now I'm talking to that. Okay, but thank you. I'm only talking about Grassmannian and k-planes. Okay? You give me one that's complementary to a particular U0. For example, W0 here. And now I look at all movements which stay complementary. And you see this is clearly HOM, because here's W0. I put an arrow here. That shows you how to teach engineering mathematics sometimes. So here's W0, here's U0. Okay? So that's the k-dimensional subspace, that's the n minus k-dimensional subspace. And you see here is W, someplace in there. And if you have W someplace in there, it's the graph of a linear mapping from W0 to U0, right? The condition that it does not intersect U0 is the condition that it really is a graph of a linear mapping from, yeah? Linear map. So, as you know, home W0 to U0 is a beautiful vector space itself. You choose a basis, you know what it is. It's, well, it's this. Right, because you choose a basis, it's a matrix, and it's in, I have to think slowly whether it's a K times n minus K matrix or n minus K times K matrix, depending how you think about it. Okay, so you see this chart is a huge chart. It's a big copy of Cn, and you see it covers almost everything. In the Grassmannian. Right? Because if you take any subspace, you can move it slightly and make it complementary. Right? So this is an open dense subset of the Grassmannian. Okay? Its complement is defined certainly by a determinant condition or some condition of this type. So you see that its complement, and you will see it in concrete calculations, is defined by an algebraic equation. So its complement is closed, defined by an algebraic equation. So everything is algebraic. We say that a subset is Zariski open if its complement is Zariski closed. And in this case, the complement is Zariski closed because closed means it is defined by algebraic equations. Please understand, there is no blah blah in topology, set theory topology. The definition of a closed set is not a priori just some fancy axiomatic topology. It comes from the fact that in every situation you are in mathematics, you know what the functions are and what the functions that should be continuous. The definition of a closed set is the zero set of a function. In the usual topology, you're dealing with continuous functions. Yes? And a closed set is what you think it is, right? Any closed set in the usual Euclidean topology is the zero set of a continuous function. It's even the zero set of a smooth function. So, yes, you see what I'm saying? Closed sets are zero sets. In algebraic geometry, closed sets are algebraic sets. They're defined by rational functions or polynomials. This great big thing here is what we say is Zariski open and Zariski dense in the Grassmannian because its complement is small and Zariski closed, and Zariski closed means its complement is obviously, you can define it with some sort of algebraic operation here, right? It's just that these two spaces intersect. That's going to be some linear dependence, right? And linear dependence is going to be defined by some determinant condition. Yes? So this complement will not be linear, but it will be easily defined. Okay, that's already, you see, we're getting, I promised you, these are the first examples of algebraic geometry. You're getting to an area, these Grassmannians, that you have an example of the so-called Zariski topology, where the open sets are complements of sets that are defined by polynomials. you can, maybe I will give you some exercises for you to have some fun. You can compute the change of variables here and see that, change your coordinates here and see that it's rational. I'm going to do it now for projective space. So, the projective space is particularly simple. It's particularly simple. And the reason is that if you have W one-dimensional, say W0, you want to take a neighborhood of W0 like here, look at all movements of W0, it's one-dimensional. So what you need is, you need U0, one codimensional. Right, let me draw the picture here so that you maybe don't have it over here. So here is a one-dimensional line. Let's call it L for line. Okay, it's a line. Now I put an arrow again. There is no natural ordering on the complex numbers. So L0. And the complementary thing, U0, is one codimensional. And the big advantage of one codimensional is U is f equals 0 for f, a linear function, on V. And f is not uniquely determined. It's uniquely determined up to a constant multiple, but is more or less uniquely determined, right? So there's a big advantage. So L intersect this thing is trivial. Well, many things is that, for example, it means that f restricted to L0 is not 0 in L0 star. Right? It's the statement that when you restrict it, it's not 0 in the dual space. There's a restriction mapping. You agree? There's a restriction mapping from functionals onto linear subspaces, and if you're unlucky, this restriction mapping has a kernel. In this case, it could have a kernel. This means that if and only if L0 is not contained in the kernel of this restriction mapping. Okay, so this simplifies things somewhat dramatically.
But Professor, to ask, what does the notation mean that the set of f equals to 0?
Oh, the notation f equals 0. Yeah, thank you. This is my private notation. Maybe I'm sorry. I quite often, so Sintal's question is this, you're asking me what does this mean?
Yeah.
Okay. This is the set of vectors v in v so that f of v equals 0.
But then, since the v is in the dual space of v, then u0 has nothing to do with L0. I think it's strange for me.
Well, this, I don't know where, let me just go through this and you stop me where I say nonsense. Okay, this is contained in V, right?
Yeah.
Okay. So, oh, I think I know what you mean. This is for some fixed element of V dual.
Oh, fixed,
Yeah, that's the confusing thing. So for some f, a fixed element of the dual, okay? So I give you something codimension 1, and you say I want to define that by a function. And I say, well, we're really lucky in this situation because it's codimension 1. It's defined by a function that's essentially unique, right? Right, up to a constant multiple. If it's codimension 2, like in this Grassmannian thing, it's defined by 2 functions. But the uniqueness question, you see what I mean? Uniqueness starts to get a little bit more difficult. And here you have the big advantage of uniqueness right off the top. It's just up to a constant multiple. Are you okay now? Yeah, thank you. Okay, so that's the picture. We're looking at lines here that are not contained in the 0 set. So the standard way to do this is to take a basis and take special sets associated to this basis. So the standard method, coordinatization, via a basis. And this basis, I write, my notation for a basis, an ordered basis, is this kind of bracket. And here, for a reason you will see in a minute, I'm going to take this vector space to be n plus 1 dimensions. So this is a standard of a basis of V. Okay. And just like here, when we take this matrix, if you would really take a matrix here, you would get a k by n minus k matrix. Here we're going to get just a vector because the number k is 1, and that's going to follow here. So this is going to be parallel to that, only a very simple case. So if you take it, let's write very carefully, a vector has coordinates z0, Zn of this vector. Believe it or not, Z1 through Z0 through Zn are linear functions. Right? This is fundamental. Well, we have linear functions, and I told you what we should do here. When you have a linear function, you should look at an open set where that function doesn't vanish. Okay? So let's say, I don't know, I've got so many letters going here. Let's call it A, B, C, D, E, F, G. I don't know. I don't know, let's call it B, Z, oh. You're going to hate me. I'm going to change notation slightly. So I'm going to let Uj be the set. It's not the same as this notation here. Okay, Sintal, this is where I changed the other way around now. Okay, that's the relevant set, right, where that thing doesn't vanish. Over here, okay, fine. So I take L here in Uj, and I take V in L, and I write it down. Oops, I'm sorry, 0En. And I know Uj doesn't vanish, so I'm tired of writing J. Let's write U0 doesn't vanish. Right, I mean, it's nothing special about U0, U2, or U17. U0 doesn't vanish. Z0 doesn't vanish. Aha, that doesn't vanish. Aha, that doesn't vanish. I'm going to map this vector to z1 divided by z0, zn divided by z0 in Cn. Again, take a bunch of open sets. These are complementary to something like that. That's good. Where these linear functionals don't vanish. I take a vector, take a line in here, and take a vector in that line. Okay? I can do all of this. This is all legal because I said z0 doesn't vanish. Right? This is all legal, but the key thing is this is defined on u0 because it doesn't matter which element I took here. If I take another one, say another one v tilde here, then I would have z0 tilde, e tilde, 0 tilde, zn tilde, en. And these two vectors, these are two different things. This is a one-dimensional space. Here's v and here's v tilde. The difference between v and v tilde, multiplicative is some factor, but I divide it out by z0, and that factor vanishes. It's projective geometry. The factor vanishes. So this is really defined on u0, and it is a homeomorphism to Cn. You get all possible vectors here. So you see, in this case, well, this is exactly what I'm finding here. You see, it's C, okay, I don't know what's going on here. There's some numbers here. Actually, here would be n plus 1, right? Because I took n plus 1 dimensions. So it's 1, n plus 1 minus 1 to Cn. So this is the matrix here. This is the matrix in this degenerate situation. So the coordinatization, if you choose a basis, is given by dividing out by where you're allowed to divide, namely on this open set where you're allowed to divide, you divide out and you get a map. So we should check what change of coordinates is. Just for fun. So we have u0, let's look at change of coordinates. Say from u0 to u1. Okay. So the way to do this is this. You have a vector here which is of this type, and you send this here to z1 over z0, to zn over to z0. And you send it here, this is the u0 coordinate, and u1 coordinate. So this thing spans the space L. And here you send it to z0 over z1 to, let's see, z2 over z1, zn over z1, right? And you see what the map is. This map is multiplication. What do you have to do to go from here to here? you'd have to multiplication by z0 over z1. Right? So, that's the rational math. Okay. Projective space. Okay. Now, concretely, let's look at P1C. Okay, so now, maybe I should say this, so we notation, if you have a basis here, we write Pn, P of Cn, you see, because we've identified this thing with Cn, and we often write this as PMC, so the complex projective space. It's n-dimensional, obviously, because these values here are in Cn. Okay. And you may not like this notation. Some people put the n up above, and I do not like that notation because then I don't know what to do with this. If these guys do this, and you do this, then you have to do this. And I don't like that. So I always put the n down below. So that's P and C. So P1 of C is one-dimensional, and this is a Riemann sphere. Maybe we should make this identification. So what am I doing? Say it again, please.
Isn't it just circle, one-dimensional?
No. He asked if it's a circle, and that's a good question, but that's over the real numbers. But he asked about this being a circle. So you see, if you start with V over the real numbers, R2, here was C2. Okay? And in R2, here's R2, everybody can look at it on the blackboard, and I'm allowed to put an arrow here, finally. Right? And you see, here's a circle, and if you're looking at the one-dimensional subspaces, yes, they each intersect the circle in 2 points. So the projective space, P1R, now R, is S1 modulo Z2, right, because of the opposite identification. And S1 modulo Z2 is obviously, not obviously, but is S1 by the map that you like, namely Z goes to Z squared. That makes that identification. So, I'm glad you made this remark. This is definitely not the circle. The way to think of this geometrically along the same lines is that we are in V equals C2, and in C2, this is the unit, these are the vectors of unit length, right? And in C2, we have the three-dimensional sphere, which is the vectors of unit length. And it's difficult for me to draw a three-sphere in 4 dimensions, so I'll draw it as if it were a 2-sphere. So this is the 3-sphere, and now you have a plane which comes through here. This is a complex line, and this complex line intersects the 3-sphere in a circle. Right? Here you intersected the real thing in 2 points. Okay, well, that's just the fact that the unit sphere in 0 dimensions is not connected, and that's a fundamental fact. I'll say it again. The unit sphere, the 0-dimensional unit sphere consists of 2 points. Right? The 0-dimensional unit sphere. So this 1-dimensional unit sphere is a circle. So actually what the projective space is the unit sphere modulo the circle action. So S1 action.
S3 or S.
So let me just rotations. And somebody asked a question. What?
Is it S3 or S2?
3, I'm up. So, again, Yeah, I'm glad we're going through this discussion. You need to build your intuition. I go into C2, okay? Maybe it's easier, I put it into C2, okay? In C2, the unit sphere is three-dimensional, because it's R4. Okay. Now, projective space is the set of all one-dimensional subspaces. Unit sphere, you see it there, right? You take a one-dimensional subspace, it doesn't intersect in 2 points because it's complex, right? It intersects in a circle, right? And that circle is just a rotation. I mean, you just rotate around in that sphere. So, P1C is the set of one-dimensional subspaces of C2. And each subspace intersects the sphere in a circle, so you have to mod out by the circle, which is just modding out by the group of rotations. Here we mod it out by Z2, which is the group of rotations in dimension 0. It's the fact that the orthogonal group is not connected. I mean, so this group of rotations in dimension 0 is a funny thing. It's a dangerous group because it's not connected. And here, this is not so dangerous. This group of rotations is just the unitary group U1. I don't know how you write this, U1. Okay? Okay? This was a good question. And it's a particularly good question because the same discussion shows that P of E in general is compact. Well, why? It's the same thing. You just have the big sphere, and you have the one-dimensional subspaces, and they intersect in a circle, so it's the big sphere modulo this rotation action. Well, that's compact. You can also check it directly with the topology, but that's that. So those are the projective spaces. I would like to speak just a little bit more. But yes, I'll just speak a little more. We started basically. So let me make a summary and then make a few more remarks for this morning session. So summary. I haven't proved it, but in fact, you will easily check that these Grassmannians is a compact algebraic manifold. This means its charts are the complement of sets defined by algebraic equations, so they're big charts, and the transformation, the coordinate change, is given by algebraic functions. Here the coordinate change is given by the simple rational function. Okay? These are the best manifolds you can think of. We will concentrate on projective manifolds. These manifolds are i.e. there are complex submanifolds of projective space. And if we choose coordinates, B and C. Okay? This is the classical study of algebraic geometry. The study of submanifolds, B and C. So, just because you would like to know that this is not some empty subject, an example of a theorem that we will prove every let me even here use a word, so every compact Riemann surface can be realized, so I have to tell you what that is. This means a connected one-dimensional compact complex manifold. So any compact manifold of dimension 1 can be realized in P3C. So, to convince you that algebraic geometry, this is an analytic object, realize in P3C as an algebraic submanifold. That means defined by algebraic equations. Emphasize again slowly. If you start with complex analysis in one variable, everybody in this room understands what that means. It means you are interested in holomorphic, meromorphic functions in one variable. For example, you look at a torus. I'm going to look at a torus. For example, you look at a torus. Well, that's easily seen to be a complex manifold. Maybe you even see it in your course in one complex variable as C modulo a lattice. Weierstrass was interested in this stuff because he was interested in the multiply periodic functions on C and what differential equations they sum. Weierstrass realized that the following differential equation, which is satisfied by his famous P function, maybe you've seen these interesting differential equation, which is satisfied by the Weierstrass P function. If you haven't, you will see it in my course. Yes? Which is, this is a meromorphic gamma periodic function. This is its derivative. This is the first interesting example of an differential equation which is coming from the flow of waves in shallow water and the flow of plasma in physics. This is the first interesting differential. You see, it's nonlinear. This is very close to what we call the Codevector-Riesz equation. Weierstrass realized this, and he was very interested in this function. It is a function that's highly analytic. It is a function that's incredibly analytic. I'll write it down. Oh, I don't know, up to a sign, it looks like this. I take out 0 out of the lattice, and I make it multiply periodic, and that's terrible because it doesn't converge, and so I make it converge. This is the Weierstrass P function written down as series development. You should never write it this way, because you can't understand it. But what it is, and I will explain this is a second derivative up to some small thing, second derivative of the log of what Weierstrass called a sigma function, which is the basic theta function here. And the theta function here, let me write theta because it's really theta, is something like this. And it's some terrible product development. You see, you want to have the function have zeros at the lattice elements. So this is in the lattice. Well, of course, you put z out here, and then you take the zero out of the lattice. And then this is a terrible thing, so you have to make it converge here. And that's where this convergent thing here, and this is the way to think of it. You start with something you want to make periodic. This is not periodic, but it is almost periodic. You log it, take second derivative, it is periodic. You get this horrible thing. And its derivative is not so bad because that kills this constant factor. It's just 1 over the thing cubed. And then you write down the differential equation that satisfies it's that. And these things are called Eisenstein series. These series are order of magnitude sum of 1 over the lattice element squared and sum over the lattice elements to the 4th power, playing a huge role in analytic number theory. This is very, very exciting. Yes. And the point is that using these functions, you realize this torus as a cubic curve in P2. Again, you start with a huge analytic theory, which is important in physics and analytic number theory and all sorts of things, quadratic forms and so on. Yes? Nowadays, in modern coding theory, this is fundamental for what we call IT security. All basic codes are made with these so-called elliptic curves. And what goes on here is a cubic curve in P2. You can see the cubic equation appearing here. But it appears here in the differential equation. It is a cubic curve in P2. Every analytic object in one dimension, if it's compact, is an object of algebraic geometry. Every algebraic geometric object is automatically something analytic because you can look at the local coordinates. You can forget that it's algebraic, just look at the local coordinates holomorphically. This is an example of Gaga. Okay? An example that you do not stay in dimension 1. Yes? You go into higher dimensions and look. Okay? It's very, 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 very beautiful. Okay, I think I will stop now, and then we will start again this afternoon at 3:45. Yeah. Is that all right with you? That's a pretty good time, right? Yeah. It's okay?